So in our next talk, Kostyantyn will be telling us about phase transitions in random circuit sampling.
Hello. Okay, this seems to be working. So my name is Kechedzhi. I'm a theorist at Google's Quantum AI. And I'll talk about this phase transitions in random circuit sampling. I will mention some theory of the experiments. The heavy lifting was done by Alexis Morvan and actually Xiao. Me, who was just up here. And I would like to acknowledge all contributions of all these people and the support from Quantum AI in general. So the outline is on the slide. The motivation, in some senses, asking a question is at what level of noise, if we are given n qubits, at what level of noise can the whole Hilbert space be still useful? Right? And I will argue that these questions, we can learn something about this question and answer it to some extent using this observation that there is this noise-induced phase transition that manifests itself in the cross-entropy benchmark. And then I'll show the experiment identifying this noise-induced phase transition and discuss implications for the spoofing of this XEB and the experiments with quantum advantage. So the general idea is the competition between entanglement and the growth of entanglement and noise. And since this is a mixed audience, I will define a little bit the setting we're working with. So we're thinking about some set of qubits that are subject to single qubit gates and 2 qubit gates, right? And we pick, for example, an iSwipe as 2 qubit gate, and the single qubit gates are chosen at random. And if it is well known that if we take this circuit sufficiently long, if the depth scales with the system size, this will converge to, will approximate a random vector, right? So this is kind of, we expect from a random vector as a typical random vector to be nearly maximally entangled. Whereas the noise does something exactly opposite. It drives the system towards maximally mixed state. And how much entanglement we can generate in the system is actually a competition of this two processes, and that's why the question arises, right? How can we actually entangle all possible qubits? Or can we actually use, even if we have a large device, is it working? Are we actually using only a small subsection of qubits effectively, right? And I will use this linear cross entropy as a particularly useful quantity that gives an answer to this question, right? In XEB, this cross entropy benchmark, what we are doing is we are again applying the circuit that I described. And what at the end of the circuit, we measure in a computational basis. So we observe some bit strings called S with some probability of the bit strings. And what we do is actually we assume that we know the exact value of PC, and we compute this quantity, right? Given the observed bit strings in the experiment, right? And this is a way to check if the experiment reproduces the circuit we wanted, right? And approximately we can say that we're sampling from the experiment with some experimental distribution. And this kind of like a correlation function between the correct answer and the experimental, actually exponentially sensitive to errors, which is why it's very good. So an instructive example is the global depolarizing channel, right, where the density matrix is just simply fidelity times ideal density matrix and then maximally mixed state, right? In this case, if we substitute this into the XEB, we get the answer that is fidelity, right? But this is kind of, we had to assume here seemingly that the noise is globally depolarizing, right? In practice, the noise is local, right? Acts on individual qubits. And therefore, there is a question whether this is always true, that XEB is equal to fidelity, right? And a way to approach it, right, as a theorist, is to consider a model where we can actually make a progress by hand, right? And this model is shown here. We call it a weak link model in one dimension. So what is assumed here is we have a system of qubits, A and B, and we split it in 2 parts. In each part, we assume is kind of does a random circuit and approaches the random statistics really well. And then between this, To subsystems, we apply a gate very rarely, right? Once in a period t, right? And then there is some noise that is characterized by this noise in a fidelity of a single layer, right? That from perturbation theory, we might expect, since each subsystem is approaching chaos, we expect the global depolarizing channel to work, and then XZB would converge to fidelity, as we expect. We can consider a completely opposite limit, right, when we actually take this period to infinity, so we never apply this ISWAP gate, and then the density matrix is obviously a product of the two. And in this case, the XZB will contain the fidelity, but also it will contain contribution for the terms where in one half of the system we have identity, in the other half we have Porter-Thomas. This gives this fidelity that depends only on half of the system, so which appears much higher and might dominate. Now, if we assume that this period is finite, not infinite, then we actually have a competition between these two terms, where lambda is basically the probability to entangle the two qubits. O1 minus lambda is the probability. So this lambda defines basically convergence rate to the Porter-Thomas distribution, right? And now we see that we have two exponential terms that are competing against each other. And the competition is controlled by this parameter f, which is the fidelity per layer. And two competing exponential terms suggest a discontinuous phase transition, right? So we expect that if the fidelity kind of is per layer is sufficiently large in comparison to this probability to entangle the two parts A and B of the system, then the XZB will converge to fidelity, and in the other limit, the XZB will converge to something that's, in this simple case, is just square root of the fidelity, so something entirely different. And this is kind of a very simple argument, but we can actually make it rigorous by taking advantage of the fact that circuit averages of the quantities like XZB can be analyzed theoretically. And the idea here, if we look at, again, a linear XZB that I just defined earlier for n qubits and depth d, this is a quadratic quantity in terms of the probability. And in this case, the averaging over circuits is particularly simple. And what it does for us, if we think of XZB as characterizing a circuit shown here, which consists of some set of qubits subject to single and two-qubit gates and measurement at the end, this XZB, after averaging, can be thought of as a classical spin model. And in fact, the XZB itself is a partition function of a classical spin model. And intuitively, like this is actually an exact mapping, and intuitively we can think of a spin, meaning that a qubit at a given moment in time and in space is either in a Porter-Thomas regime or in a maximally mixed state. So that would correspond to this, what I denoted here by filled and empty circles. And these are only two possibilities for each qubit after averaging. And therefore, we can introduce a basis that just looks like a classical spin 1/2. And then in this, after this averages, what happens is that the entangling gates like ISWAP would correspond to interactions between spins. So this would be an interacting spin model. And the noise can also be described, even local noise. And after averaging, the noise will appear like a local field. Now, this model is remarkable because once we do the averaging, each configuration of this effective spin model can be associated with a non-negative weight. And then this makes actually, this XZB is actually a simple partition function for a classical spin model, which can be analyzed easily. And then one caveat is that this mapping actually depends on what kind of single qubit gate ensemble we are taking. Right? What I described to you with spin 1/2 corresponds to the choosing 1-qubit gate to be uniformly random, and 2-qubit gate some fixed gate. In practice, in the experiments I will be describing later, we will be using a discrete set of gates, 1-qubit gates, which correspond to pi/2 rotations around some axis in the equatorial xy plane of the qubit. And in that case, the spin, the classical partition function, can have a much more complicated form. Particularly, it corresponds to spin 1 rather than 1/2. There are 3 possible states for a qubit. And this actually affects the convergence significantly, so it's an important detail. But within this classical, now statistical model, we can define the phase transition rigorously and prove that it's actually a first-order phase transition. Now, I described what happens in a weak link model, where we had 2 parts of the system connected by some gate that's kind of weakly entangling them, and that corresponded to this picture that already looks like a competition of 2 exponents, or like a first-order phase transition. It is actually possible, in the language of the spin model, to generalize this to a chain of weak link models and obtain, which can be solved by a transfer matrix technique. We can obtain actually an explicit expression for XZB. This chi is an XZB for given n number of qubits, d depth, and epsilon level of noise. Right? And in this expression, we can take thermodynamic limit. And the limit we're interested to take is taking depths to infinity, but keeping the layer fidelity, this f here, fixed. So we fix the error rate per qubit times number of qubits, right, as some constant. And it is natural actually to rescale the depths as logarithm number of qubits. And in this rescaled quantities, we actually can obtain explicitly a transition critical line, right, as a function of alpha. And this is the phase diagram we would get in this, where the axis correspond to vertical is this alpha, normalized depths, and the horizontal axis is this error per cycle. All right, so, and this is the phase transition now is described by this specific dependence on the depth. And we can actually take a limit of no noise and recover a known result for the anti-concentration point that was obtained before in the literature. And this is where the XZB becomes close to its limit. Right? The difference between XZB and its limit scales to 0 with the system size. We can actually do that. Oh, wait, one thing I forgot. So now the picture I was describing you for the weak link model actually translates to a one-dimensional chain. Right? The competition in the noise in a regime where XZB equals to fidelity. So we have all qubits entangled, and in a strong noise regime, we have a state where some part of the system is entangled, and some part is in a mixed state. And this is characterized by this single domain wall. Right, that's in some sense this state has only one weak link. You can think of it in terms of magnets as a single domain wall state. So this is the state that's most likely to compete with the weak noise regime. And if we increase noise gradually, this is the one that will dominate after the transition. Now, we can do the same analytically in 2 dimensions, and remarkably obtain actually also explicit expression for XZB, and show that the phase diagram remains the same as long as we renormalize this alpha with keeping in track particular period of application of gates in 2 dimensions. And then, so how do we identify this in the experiment? We actually take XZB and compare it to fidelity directly. And we expect this quantity to either converge to 1 or to something that is exponentially small. So we can actually do as a function of this layer fidelity, we expect this finite size scaling diagram. As we change the depth, this ratio actually behaves differently to the left and to the right side of the transition point, and therefore we get this set of curves that likely to almost intersect at one point. And that can be actually observed directly in the experiment. So in the experiment, what we do is we can control the noise we have like the best noise that's possible, and we can add additional noise, right? And that in this way tune through this transition. And luckily, our devices are in a weak noise regime, which is the whole point for us to study this. And we can actually directly observe these ratios and see this finite size scaling points for this order parameter, which is taking XZB and comparing to the global depolarizing channel or expected fidelity, which would be just the product of all gates, right? And we can do it for different parameters of the circuit, different strengths of the noise. Can also do it in 2 dimensions and observe these crossing points in 2 dimensions. And what we learn is that, in our devices, we need to increase noise to get to this transition. Now, there are 2 reasons why this is remarkable. First of all, this is an out of equilibrium quantum phase transition that is sharp in presence of noise, which is kind of the opposite of what we usually expect for out of equilibrium quantum phase transitions, which are typically broadened by noise. So it's kind of a new type of the transition, yes. It also, for us, kind of at Google Quantum AI, it has implications for using XZB as a metric of quantum advantage. Right? Many of you would be familiar with this, but the idea is that we can run a random circuit and produce samples from this random circuit. And XZB would tell us if the samples are produced from the correct distribution. Right? And we can estimate in the experiment, and this I'm showing this latest data, from 67 qubits, and the largest circuit we did at the time of this paper published, this 880 iswaps, a total fidelity of about 10 to the minus 3. What we see is that this XZB is a nice exponent, and we can extrapolate it, right, or estimate and verify this extrapolation by looking at circuits that are very close in geometry. And the idea here is that this XZB tells us how well our device produces the random circuit output, right? And this corresponds to a very large kind of alternative classical simulations, right? Now, there is in the literature, there was a proposal to spoof this result. So basically produce bit strings without doing the actual computation that would look as good as in the metric of linear XZB as output of the experiment. But the spoofing actually takes an advantage of the noise. That it kind of exploits the fact that noise prefers these local correlations, as I was describing. And we can actually put a bound as a result of this intuition on the spoofing, right? We can say that the maximum XZB you can get from spoofing is basically the difference between XZB and the infinite time limit of the XZB at a given time. And this is generally scales as an exponential. And we actually remarkably can extract this exponential for our specific circuits using the following trick. For our 1 qubit ensembles, the Clifford version of it and non-Clifford version of it realize exactly the same dynamics of the XZB. And therefore, on Clifford, we can easily simulate. So here on the right, I show the behavior of the XZB, which we fit to an exponent to extract lambda, right? And for this lambda, we can, with confidence, say that our devices are well beyond what can be spoofed. There is one other trick that was proposed in the literature, is that you can improve the spoofing by using the fact that if you have a model of wave function, right, that you hold in memory, you can use kind of sampling from a distribution that's non-linearly connected to it, right, because you know the distribution. But however, for Porter-Thomas, this comes with an overhead, and this procedure can only give you a logarithmic prefactor in front of this exponent. So if we combine this all together, what we get is that the best possible spoofing for these circuits will be orders of magnitude than our fidelity. Yeah, and I think I'm out of time. So yeah, if you would like to see the details, please have a look at this paper.
Thank you. We have time for one question. Michael?
Can you explain again how you have a spoofing phase and a non-spoofing phase? I saw this in your phase diagram earlier in the talk. You
Yeah.
had spoofing, right?
Yeah. Spoofing also fights against an exponent, right? And if you have a transition basically where the whole sample is entangled, right? And transition to the state where the XZB is dominated by local correlations. So in this state where the XZB is dominated by local correlations, you can actually do spoofing because your XZB is actually given by those local correlations, so you would exploit that in spoofing, right? The transition is not exactly where the noise-induced phase transition, but it is closely related to it. So that's why we can put a bound.
All right, let's thank Kostya once again.